All right, we're in section 9.6 for my BC kids, and we're continuing to look at vectors and parametric equations, but now we're going to add motion into the picture. And a lot of this is going to dig back into your A-B roots and make the same comparisons between position, velocity, and acceleration that you made back in Calc AB. We're just going to apply it to a vector type situation. So position is, they call it R of t, but it's your x component and your y component. Velocity is the derivative of your position. So that's x prime of t and y prime of t, and acceleration is the second derivative of position, first derivative of velocity, and that's going to be x double prime of t, y double prime of t. Speed, they use this crazy notation for speed. It is the derivative of velocity. Derivative of, it is velocity, the absolute value of velocity, or the first derivative of position. And here's how you find it. This one is not a vector for our situation. So it is the square root of x prime of t, quantity squared, plus y prime of t, quantity squared, and that would be, that's it, not a vector. Okay, so we want to make note of that. I'll put it down here. Not a vector. So they want us to, in number one, find the velocity vector, speed, and acceleration vector for the particle that moves in the xy plane described by r of t equals 5 sine of t over 5. For the x component, y component is 5 cosine of t over 5. And so we are going to do our work, right? We're going to find x prime of t so that we can find the vector. You can't get through to the acceleration vector without obviously going through the velocity vector. And so we're going to find the velocity vector first by finding the derivative of the x component and the derivative of the y component. So here we go. It's going to be 5, the coefficient. Derivative of sine is cosine of the same angle. And it is then times the derivative of the angle. Well, the derivative of t over 5 is 1/5. So there's your x component. Let's go to the y component. Well, the derivative of cosine is negative sine, so that's going to make this a negative 5 sine of t over 5 times 1/5. And so let's put it together into its vector component. V of t equals 5 times 1/5, they cancel each other out, so I get a cosine of t over 5 for the x piece. And for the y piece, again, the 5 and 1/5, they cancel each other out, but I'm left with a negative sine of t over 5. And so there's my velocity vector. We've got that down. If I go for the acceleration vector, I think I can fit that right under here. Same idea, I'm going to take the derivative of the x component from velocity and the derivative of the y component from velocity. Derivative of cosine is negative sine. I'm going to leave some space. Negative sine of t over 5 times the derivative of the angle, which is 1/5. I'm going to put that in the front. Same thing is going to happen for the y component. It is going to be a negative, leave a space, derivative of sine is cosine of t over 5 times the derivative of t over 5, which is 1/5, put it in front. And there you go. Now you got the acceleration component. And then the last piece they asked us to find is speed, so I'm going to go for the speed here. Well, that's this big old square root. And that square root would be the cosine squared of, you're going back to your velocity vector here, the cosine, it's actually the cosine of t over 5 squared. I'm just going to write it this way and you'll see why in a second. Cosine squared of t over 5. And then same thing with my sine plus the sine squared. Technically it would be negative sine times negative sine, but they turn positive. Sine squared of t over 5. Oh, you need to see me. Here you go. So here's where I'm at. Now let's think about this for a minute. I think we've seen this come up in other sections previous to this. If I have sine squared plus cosine squared of the same angle, then the Pythagorean relationship comes into play. Sine squared of an angle, cosine squared plus cosine squared of an angle equals 1. So really this would be the square root of 1, which is 1. And there's your speed. So you've got to pull back that old Pythagorean identity and what you're basing it on. It says sine squared of theta plus cosine squared of theta, whatever that angle is, as long as they're the same, it's going to equal 1. So that was the identity that we used to be able to do that. All right, quick review. When does a particle speed up? Does this particle speed increase or decrease? It's speeding up when they have the same signs. We've seen that before in AB. And they are slowing down when they have different signs. So you're comparing the signs of velocity and acceleration. If they are the same, it's speeding up. If they are different signs, then it is slowing down. Number 2, if r of t is this vector, find the velocity and acceleration at time t. Okay, so let's find velocity first. This one's easy peasy. This one is derivative of these are just a little quick little polynomial things. So 6t squared plus 1 and 2t. There's my velocity vector, my acceleration vector, derivative of that, 12t, and it's comma a 2. 12t and 2. Wish every question was that easy, but they're not. So here you go. Find velocity and acceleration at time t, you got it. Find the speed at time t equals 2 for this vector. Well, speed comes from velocity, so we need to find the velocity vector. Let's do that first. Velocity vector is going to be a 3. And then it's going to be, all right, e to the negative t squared. So it's going to be e to the negative t squared times the derivative of the power, which is a negative 2t. Maybe I can clean that up and make it look a little bit better before we go speeding for this thing. 3, and then it's a negative 2t e to the negative t squared. That would be my my velocity vector for this. And I'm going to take that and I'm going to kind of calculate out what speed would be from that. So speed, remember, is this big old square root, and it is the x component, first derivative squared. That's pretty. But then we get to the y component, and that's going to be a little bit more messy. So let's think about this for a minute. It's going to be, I'll write it out, negative 2t, I'll leave it with t's for the moment, e to the negative t squared, just so you see where this is going. I keep wanting to put a dt after that, but it's not an integral. It's just a regular old square root. All right, so here's your square root. 9, right? 3 squared is 9. If I put a 2 in here, let me find my colors. This will work. If I plug a 2 in here for this, right? Because it said when t equals 2. And if I put a 2 in here for this, let's see what that's going to change this whole thing to. So it's plus. When I square the negative, that's gone. 2 times 2 is 4. I'll put it this way first. E to the negative 2 squared is 4. To the negative 4. And that whole thing is being squared. So I replaced my t's with 2's. And now I go to my handy dandy calculator and I say, Mr. Calculator, what shall this come out to be? And so I take the square root of this and put my e's in, and I get the number, and it's actually 3.001 or so. You could say it's an estimation. If you want to do those squiggly equal signs, that's cool too, because it's not an exact answer. You rounded it, and there it is. So total distance traveled is the next thing they're going to bring up, and guess what? It's really similar to what speed is, but now you're looking at it between two values, an A value and a B value, a starting place and a stopping place. And so this one, how you find the total distance traveled is to take the integral, right? If I want to know a distance, I'm going to look for integrals, and that's going to be the integral from A to B of, now what's another way I could say this? This is the same thing as speed, right? So if I take the what I know about speed, speed is going to be the square root of x prime of t squared plus y prime of t squared. Now I need the dt. Right now I need to say with respect to t. And so that's what I'm looking at. So that's the total distance traveled by a particle. If we flip the page, we're going to try two more examples. See where it takes us. Number 4. Given the velocity vector of the particle v of t equals 2t minus 1 and 5, and the position of the particle at time t equals 0 is 1, 2, find the position when t equals 3, and what's the total distance traveled on the interval from 0 to 3. There's a lot going on in this question, right? So let's go with thing number 1. Let's find the position. Well, the position is going to be, they give me velocity. Now think about this from back in Calc 1 and Calc AB. If I'm at velocity and I want to go backwards to position, what do I need to do? And so hopefully you are thinking, well, geez, if I'm trying to get to position, then I need to take the integral of each of these pieces. So I'm going to take the integral of 2t minus or plus 1 and the integral of 5. So let's try doing that first. So position is going to be, if I'm 2t, I'm going backwards, I add a power on, divide by the power. So 2t squared over 2 is t squared. And if I have a 1 plus 1, that's just plus a t. However, I still need my plus c, right? It's an indefinite integral, so I need to put the plus c with it. And this guy over here that's a 5, he's going to be a 5t plus c when I take his integral. Well, let's think about this for a second. They also gave me this coordinate right here. 1 is the x component. 2 is the y component, what it would equal, what the position would be. So if I take this x piece and set it equal to 1, 1 equals, I'm going to do this out kind of the long way this first time, t squared plus t plus c. What did they tell you t was if you're at 1, 2? And they told you that t was 0. So what that actually does is zeroes out these pieces. And so this guy becomes a 0. This guy becomes a 0. And so you know that c is 1. And so as you're putting your position vector together, you know that you've got p of t, your position. You could use r of t, whatever you want to say, but I'm using p for position. Is going to be the equation t squared plus t plus c, my c value of 1 plus 1. And then you're going to do exactly the same thing for the y component, but the y component equals 2 according to what they told you. So you're going to say 2 equals 5t plus c. Again, t is 0. Knocks out that whole piece, so you know you've got a c of 2. And so putting your position together, here's your component for this. It's going to be 5t plus 2. All right, so find the position. We just did. Now it says find the position when t is 3, and you're like, okay, well that's easy. All I have to do is plug it in. So here's what it's going to be. You're going to plug in a, find the position when t is 3, so you're going to plug it 3 in for your t's. 3 squared plus 3 plus 1, 5 times 3 plus 2, and that gives me the vector of 13, 17. All right, that takes care of the first part, and then it says, well, what's the total distance traveled on the interval from 0 to 3? Well, that total distance is like the formula we just wrote down a second ago. If I'm looking at total distance, I'm looking at the integral distance, if I could spell. I'm looking at the integral going from Well, if I'm looking at this, it's from 0 to 3. I want to know where it is at t equals 3. So 0 to 3, the integral a to b of the square root of the first derivative squared plus the second, the first derivative. I'm going back to my velocity vector, and I'm using these two values in it. So I don't need the position anymore. I'm going back. I need 2t plus 1 squared plus 5 squared. And that would be with respect to t, so dt. All right, so I go back to my calculator. And I go to my calculator and I say, all right, Mr. Calculator, tell me what this integral would be. And it comes out to be approximately 19.65. Here's another way that you could look at this, and we talked about this in class. Some of you liked this method better. I think I'm going to put it up above. Up above. Another way that you could have done this for your position vector, you could have done, look at this, 1 plus the integral from 0 to 3 of 2t plus 1 dt, comma, as your x component, and 2 plus the integral from 0 to 3 of 5 dt. And that would have given us the same value that we got down here of 1317. So a different way of looking at it. I kind of like keeping it consistent with find your C value and then plug it in. It just, for me, that seems to make more sense. But this also works to give you the same 1317 answer. All right, number 5, last example. A particle moving along a curve so that its velocity for time t is greater than or equal to 0 is given by this vector. For what values of t is the particle moving right? And for what values of t is the particle moving up? Well, let's go back to Calc 1. If I want to know when something is moving to the right or left, that's based off of, I hope you're knowing this, that's based off of your first derivative. So it's when your first derivative is greater than 0, it's right, and when it's less than 0, it is left. However, in this case, I've got two pieces, right? I have two pieces to my velocity vector. Nice that they gave us velocity, so I don't have to actually calculate it. So I have two pieces, so which one is the one determining right or left? Think logically, right? Your x component is the one that's going to be left and right, and your y component is going to be the one that goes up or down. So I want to know when the x prime of t is greater than 0. And that's going to tell me when it's moving right. So let's think about this. Take it over here. I want to know when 2e to the negative t over 4 is greater than 0. If I divide by 2, then when is e to the negative t over 4 greater than 0? Few ways that you could do this. If you go to your calculator and graph it, by the way, this is a 4. I know I said it, but you know. If I go to the calculator and graph it, you'll see that it's always positive, this guy. It is always positive. So your answer is when t, so let me make it more specific. So moving right, when t is greater than or equal to 0. It's always moving right. And I know that from the graph of that equation. For what values of t is it moving up? Well, that's dependent upon the y component. And so I want to know when is the y derivative greater than, up is greater than 0. All right, so let's take the y component. T minus 4 over t plus 5. I want to know when that is greater than 0. Well, you can, I know I like to cross multiply, but you could also multiply both sides by t plus 5. Either way, the next thing you've got is t minus 4 is greater than 0. So if I solve that inequality, it's when t is greater than 4, the particle is moving up. All right, well, that does it for the examples that go with this particular section, section 9.6. There really aren't any that are too crazy as I'm looking through. Maybe let's go to number 9. You've seen examples for things enough in the other questions, but I don't think you'll run into a jam. Number 9 is a calculator active problem, and you're like, thank you very much. The velocity vector of a particle moving in the xy plane has components given by dx over dt is cosine of t squared, dy over dt is e to the t minus 2. At time t equals 3, the position of the particle is 1, 2. What is the coordinate of the position vector at time t equals 2? So, this is like the problem we did a few minutes ago. But this time they only want to know what is the y coordinate. Well, guess what? If you're looking at the y coordinate, you don't care anything about the x coordinate. They didn't ask you about it. And so you don't have to go there. So there's a couple different ways that we could do this. We could go and integrate the y component here, because remember they gave us dy over dt. They're giving us the first derivative here. So I can go backwards and find the position function, and then use the information I know that it equals 2. 2 equals, and that would allow me to find c. And then I could put it in and figure out what this would be. Here's the other way. Remember the way I wrote in the top of the page, the margin, top margin? It's at 2, the y component. And if I look at this, it's going to be minus, because I'm trying to go backwards, right? This is what it was at 3, and I have what it is at 2. Actually, I think when we talked about this in class, we changed this up. Well, let me think one more time. At time t equals 3, the position is 1, 2. What is the y coordinate of the position vector at time t equals 2? Yeah, we're going to go backwards, but what we're going to do, so we're subtracting it, we want to know what it is from 2 to 3. We're going to take that away. And if I take that away, it's e to the t minus 2 dt. And so we go to the calculator and calculate that out. It comes out to be approximately 2.82, or 0.282, my bad, 0.282. Number 12 was tricky, so we're going to do 12. Number 12 says a particle moves on a curve y equals 2x so that the x component has a velocity of 3t squared plus 1 when t is greater than or equal to 0, and at time t equals 0, the particle is at the point 2,4. At what point is the particle when t equals 1? All right, so let's see if we can decipher this a little bit. If I go to my x component, and I know I'm trying to get to position, they're bringing up that word position. Let's see if I can go backwards and integrate that and figure out what the x component is. X of t equals, add a power on, divide by the power means I'm at t cubed, plus 1 is plus t, plus c. Do I have information that will help me to figure out what c is? And you say yes, they gave me a coordinate right here too, when t equals 0. So I know that it equals 2 when t equals 0. So my c is 2, which means that my x component for position is t cubed plus t plus 2. So when I put my position, this is where it gets kind of interesting. When I put my position vector together, p of t, I know the x component is t cubed plus t plus 2, and the y component, ooh, look, they gave me the y component right here, y, just a regular old y, not a y prime, y, is 2x. And you say, yo, you can't leave it like that. You can't have x's in one part and t's in the other, right? That doesn't look like the right thing for vector talk. They both have to be in terms of t. So then you got to think, well, how on earth can I change the x into a t? And here's the story. This is where it's tricky, but it should be logically make sense. Isn't this what x equals? Right? Doesn't that equal x? So all you need to do to put your position velocity together, your position vector together, is to x component stays the same. Y component, multiply each piece by 2, is 2t cubed plus 2t plus 4. That's your y component, and that's what's semi-tricky about this. So let's see if we answered their question. At time t equals 0, the particle is at the point 2, 4. At what point is the particle when t is 1? So you're going to make your position formula p of 1. You're going to plug it in. 1 plus 1 plus 2 gives you a 4. 2 plus 2 plus 4 gives you an 8. And there it is when time is 1, when t equals 1. So that should do it. And if you have questions as you're working through, shoot me an email. Otherwise, I will see you in class.